In the second part of section 11.6, we're still finding the areas of regular polygons, but it's not going to be quite as easy today. We're going to actually have to use either trigonometry or special right triangles to be able to come up with the area of those regular polygons. Remember that special right triangles, we had two types of those. We either had a 30-60-90 or a 45-45-90, and they had special shortcuts to find those legs or hypotenuse. And trig, remember SOHCAHTOA, sine, cosine, and tangent. We're going to review that here, and we're going to review special right triangles. We're going to have to use those today to be able to find maybe the apothem or side length in our regular polygons. We'll be missing something we need. Remember that we also need to use those central angles. We're going to have to use those today, whether it's trying to come up with an angle to use with trig or our special right triangles. But to find that central angle, we know the angles in a full circle add up to 360, and the number of central angles in any polygon is the same as the number of sides because you draw every radius in those regular polygons, and the number of central angles would be the same as the number of sides. So to find that central angle, remember you do 360 divided by n, divided by the number of sides, and that will help us today because then we'll be able to come up with these right triangles. Remember theta is just our angle symbol, and this is going to be our reference angle. You should remember SOHCAHTOA, helping us to remember trig shortcuts, or the trig ratios, I should say. Now the sine of an angle is opposite over hypotenuse. That's the ratio we're always looking at for sine of an angle. If this is our angle, our reference angle is theta, we're looking at the opposite leg, which would be here, and hypotenuse would of course be this length. Cosine, we're looking at adjacent over hypotenuse, would be that ratio. So the cosine of this reference angle theta is the adjacent leg, which would be here, over the hypotenuse. And finally, tangent, of course, is opposite over adjacent. So the tangent of this of theta of this angle is the opposite leg over the adjacent leg. So keep in mind, we're going to use trig today. Also, a review of our special right triangles. We had a 30-60-90 special right triangle. Now this came from, if you remember, it came from a original equilateral triangle where all of these sides were the same. And we know that this side is split by the altitude. So we actually called this short leg x, and it was like our most important side because from there, the entire side of the original equilateral triangle is double that, so this would be 2 times x. And then we found, using these x's in Pythagorean theorem, we found that the long leg is x times square root of 3. And you can remember that it's square root of 3 because there's 3 different sides, 3 different angles, or a 30-degree angle in there. So there's our 30-60-90 shortcuts. If you have the short leg, you times by 2 to get hypotenuse, and you times by square root of 3 to get the long leg. If you have the hypotenuse, divide by 2 to get back to short leg. If you have the long leg, divide by square root of 3 to get back to short leg. Now with a 45-45-90 right triangle, of course this has to be 45 degrees, which also means that this is an isosceles right triangle. 2 congruent base angles means 2 congruent sides, so we called both of these x. They're the same length no matter what. And to get that hypotenuse, you just take that x and multiply by square root of 2. And you can remember it's square root of 2 because they're 2 congruent sides or angles. So if you have the legs, they're the same, multiply by square root of 2 to get hypotenuse. If you have that hypotenuse, divide by square root of 2 to get back to those legs. Now I put 3 different regular polygons below here because these are the 3 regular polygons that have these special right triangles in them. First of all, in a hexagon, when you draw 2 radii in a hexagon, you actually create equilateral, equiangular triangles. This central angle is 360 divided by 6, or 60 degrees, which means all of these are 60 degrees. And when you draw in that apothem, you now create a 30-degree angle here. You just split the 60 where these were 60 as well. So now you have the special right triangle, 30-60-90. In an equilateral triangle, the central angle would be 360 divided by just 3 central angles if we drew that third one in there. So this is 120. But, of course, when you draw the apothem in, you're now splitting that 120-degree angle So you have a 60-degree angle here, and this would have to be 30. To complete my 30, 60, 90, I have another 30, 60, 90 special right triangle. And finally, with a square, if I draw two radii, and if I do 360 divided by 4, this is actually a 90-degree. I have a right triangle. These radii are congruent, and these would have to be 45-degree angles here. Also, if I draw in this apothem, I've now created a situation where I have 45, 45, 90 right triangles again, and all three of these are congruent. So this special right triangle is used in a square. Let's combine trig and special right triangles to try to find area of some regular polygons today. So a regular decagon is inscribed in a circle. So picture a circle going around that. In a circle with radius 8 units. Okay, so the circle going around this decagon has radius 8. It's a decagon, so it does have 10 sides, if you notice. I need to find the perimeter and area of this decagon. All I have is radius. Now remember, the area formula for a regular polygon is 1/2 ANS. A is the apothem. I don't have that right now. N is the number of sides. I do have that. It's a decagon, so 10. Side length, I don't have that either. Now my recommendation for today is really I need to focus on this triangle that's formed when you draw two radii and that apothem. So I'm going to kind of do a blown up, zoomed in version of this triangle. Here's my apothem, my apothem, I don't know that yet. But I know that it's meeting at a right angle with that side. Okay, and I know that the radius was 8, so I'm just doing a zoomed in version of this. All I know is that 8 right now is the radius. I need the entire side length. I need the apothem if I'm going to be able to find the area at all. Maybe I'll do my dotted line out here picturing that whole triangle. First things first, what's a central angle measure? Because the only way I'm going to be able to figure this out is if I know these central angle measures. Now the whole central angle is between the two radii. If it's a decagon, there would be 10 central angles, so 360 divided by 10, giving me a 36-degree central angle. However, that's this like entire angle here, and I really only want half of that, so I'm going to divide that by 2, and I find out that this is actually only 18 degrees right here. Now this will help me be able to use trig. Okay, it's not a special right triangle, it's not a 30, 60, 90, it's not a 45, 45, 90, but it's an 18-degree angle at least. So I can figure out the apothem and the side length using trigonometry. Well, here's how we're going to do it. First of all, let's say I want to find the apothem. Well, what would I call apothem? Remember trig, you label opposite, adjacent, hypotenuse? Apothem would actually be the adjacent leg for 18. Good thing I labeled it as A. 8 is your hypotenuse, isn't it? For that right triangle. The trig function that uses adjacent hypotenuse is cosine. So I'm doing the cosine of the angle measure. The reference angle is 18. And cosine equals adjacent over hypotenuse, which is A over 8. To solve for A, undo divide by 8 by multiplying by 8. And what is my apothem? I'm doing 8 times cosine of 18 on the calculator. And to 2 decimal places, 7.61. I will definitely need that. Okay, next thing. I need to find the side length. Guess what? You're not going to find the side length directly. You're first going to find half of the side length, and then you will double that to get the entire side length. Now to find x, I'm thinking for that 18, x would be located opposite. And we are going to use the given one, the exact answer of 8 here, which is hypotenuse. Now the trig function that uses opposite hypotenuse is sine. It's the sine of the angle, 18 degrees, equals opposite over hypotenuse, so x over 8. And once again, to solve, x is being divided by 8, I will multiply by 8. 8 times sine of 18. I'm figuring out that x is equal to 2.47. But I want the side length, so I have to times by 2, right? Because this is only half of the actual side length up here. That's this little portion. I want a side length of my decagon. I'm going to keep that exact answer in my calculator and just multiply by 2. I get 4.94. Okay. I believe I have all the info I need now to do the area. Area is 1/2 ANS. Now the apothem I found using trig was 7.61. Number of sides is n, and it's a decagon, so 10. Side length I found by using trig to find half of the side, doubling it. Side length was 4.94. Alright, what is the area? 0.5 times 7.61 times 10 times 4.94. The area of this regular polygon is 187.97, it looks like. No units? Yeah, it was just units. Now this is area, so units squared. There we go. So use trig there to figure those out. Looks like I also wanted perimeter. That shouldn't be too hard. Perimeter, you just take the side length. Remember, we got 4.94 for the side length times how many sides there are. It's a decagon, so 10. Perimeter then equals 49.4. Just units because it's a distance. Okay. Oh, one thing that I should review with you real quick. Now you notice both of the variables were on top with the trig that I had done here. What if the variable's on the bottom? And I'm just going to do a random one. This has nothing to do with this problem. But let's say I had the tangent of 70 degrees. And let's say it was 15 over x, and you were trying to solve for x. Do you remember what to do there? Remember that you can't have the variable on the bottom. So first you multiply by the variable to get it off the bottom, and it'll come to the top here. And then since it's x times tangent of 70, you divide by tangent of 70 or whatever it would be on both sides. So actually in the calculator you end up putting the number divided by the trig function to get that variable. So just a little thing, make sure that you know how to solve with a variable on the bottom as well. But yeah, so this one, definitely some trig to be able to get my area. Alright, find perimeter and area again. This time we're finding the perimeter and area of this triangle. And we're assuming it's a regular triangle here. It's got to be. Equilateral, equiangular. Now, 5 is what? 5 is the apothem, isn't it? The apothem, which is kind of nice. Well, when I'm doing area of a regular polygon, I need 1/2 apothem, half that. Number of sides is 3. It's a triangle. Side length is the thing we're looking for. So I need the entire side length here. Well, I'm going to have to form triangles here if I'm hoping to find that side length. If I draw in this radius, and maybe kind of do the other one too, this is one of those special right triangles, and the reason why, if I look at the central angle between these two radii, 360 divided by the 3 triangles that would be formed here if I did all 3 central angles, 360 divided by the number of sides, is 120. But if this whole angle is 120, I know I'm now splitting that 120 into 60 and 60, making this angle here 30 degrees. Check it out, I've got a 30, 60, 90 right triangle here. I can use my shortcuts. Now 5 is my short leg, which is kind of the nicest one, the one I want to start with. Technically I need long leg. I need this distance here. The longer leg, you take the short leg times square root of 3, remember. So 5 times square root of 3 would be my longer leg. Hypotenuse is double that here, like the radius or hypotenuse is actually 10. But I don't need that. I need the actual side length of the triangle. Now the longer leg was 5 square root of 3, so the whole thing is 5 square root of 3 times 2. So I can multiply 5 and 2 because those are both the numbers, so it's actually 10 square root of 3 for my side length. And now I can find my area. 1/2. The apothem was 5 from the radius to the side at a right angle. Number of sides, triangle, so 3. Side length was double the 5 square root of 3, so it was 10 square root of 3. And calculator time. Half times 5 times 3 times 10 square root of 3. And I get an area of 129.90. No label on there, but this is area, so units squared. And lastly, I need perimeter. There's 3 sides, each 10 square root of 3 in length. So 3 times 10 square root of 3, or 3 times 10 would be 30 square root of 3. If I get a decimal there. Rounded 51.96. And this is just units because it's just a length or a distance. So today you're going to have to use either trig or special right triangles to be able to find the area of these regular polygons and use 1/2 ANS.